Hello, and welcome back to the second episode of my series on quantum mechanics. Today, we're going to be covering the first half of the second chapter of David Griffith's textbook on this field of study. Namely, we're going to have a few objectives to learn about today, but they're all going to center around the time-independent Schrödinger equation that I brought up a whole lot in the first video. Today's objectives include stationary states, the infinite square well, and the harmonic oscillator. I plan on covering the latter half of the chapter in a second video, since I think that trying to cram that much material into a single video would be just simply too much. Now, on to the lesson. Stationary states. We begin this section by revisiting a concept we talked about at length in the first video, the wave function, psi of x and t. We tossed it around a whole lot, we didn't answer a critical question. How the heck do we even get it? We can start with the assumption that our potential energy, V, is time independent. This allows us to solve for psi using a method known as separation of variables. Essentially, we split our function psi xt into a product of two other functions, psi x and ft. What we can do now is substitute our product back into the Schrödinger equation. Now what? Well, if you're not familiar with solving a differential equation via separation, the point is to isolate each of our separated functions on either side of the equality so that we can integrate. To do so, we need to divide both sides by a factor of psi times f. For the time being, we will call the right-hand side of this formulation e. This allows us to rewrite the value of df dt to resubstitute back into one of the previous steps, giving us this final result, all in terms of lowercase psi. This is called the time-independent Schrödinger equation. To solve, all we do is multiply both sides by dt and integrate. Doing so will yield this solution for f of t. Now that we have a way to find psi of x, we must ask ourselves, why is this method actually important to us? Griffiths gives us three reasons. A. The solutions are stationary states. In other words, although the general solution for psi xt is time-dependent, the probability density doesn't depend on t, as squaring the wave function by multiplying its complex conjugate gets rid of the exponential term, thereby eliminating time dependence in the probability density. B. These stationary states define the definite total energy of our system, the Hamiltonian H. We say that the Hamiltonian is simply the kinetic energy of our system, momentum squared times twice the mass, summed up with the potential energy V of x. As a brief aside, we can define our Hamiltonian operator, which gives us the total energy of a wave function when we apply it, as this: negative h bar squared divided by twice the mass times the second partial derivative with respect to position x plus the potential. Applying the operator simply requires that we multiply it with a wave function psi. We actually can obtain a simplified version of the Schrödinger equation when we realize that we can factor out the wave function psi in the first expression, leaving the concise equation h psi is equal to e psi. Griffiths goes along to define our expectation value and standard deviation of the Hamiltonian. One important detail to note is that the standard deviation of the Hamiltonian resolves to 0, which means that every member of our ensemble must have the same value. Consequently, every measurement of the total energy returns the value E. C. Lastly, we get a linear combination of separable solutions. This is due to the fact that the time-independent Schrödinger equation actually yields an infinite set of solutions with a different associated energy value, E. This allows us to construct a general form for capital psi being the sum of n equals 1 to infinity of c sub n times psi sub n times our exponential time-dependent function. Every solution to the time-dependent Schrödinger equation can be written in the above form. 2.2. The infinite square well. On to the next section, we'll cover a very specialized set of questions that get asked a lot during quantum mechanics courses. The case of the infinite square well. For this case, I want you to imagine that you've fallen into a canyon. You're unscathed, but the drop was immense. so immense that you can't see the top of the canyon anymore when you gaze upward. The only space you have is what you've been left with in between the canyon walls. You can try your best to climb up these insurmountable cliff faces, but the amount of energy it would take to do so would be immense. Now let's shift to our quantum case. Instead of finding yourself at the bottom of an unimaginably deep canyon, imagine a particle trapped in an energy well, sandwiched between two walls of infinite potential energy. Consequently, our particle can only exist within the area where v of x is equal to 0. Allowing our potential to equal 0 in the Schrödinger equation for this case allows us to simplify it, turning it into a second-order differential equation with a handy constant k hanging out in the front, equal to the square root of 2 times mass times energy divided by h bar. In analyzing this differential equation, we ask ourselves, what types of functions return themselves with opposite magnitude after differentiating them twice? Trigonometric ones. So, this gives us the general solution of psi x is equal to a sine k of x plus b cosine k of x, where a and b are arbitrary constants just kind of hanging around. We need to solve for these constants by finding the boundary conditions of our wave function. We have to do so by first setting x equal to 0. Doing so shows that b is equal to 0, giving us just that we have a sine kx. If x is equal to 0 here, then we get a trivial solution of psi x equals 0. But if x is some non-zero constant a, then we can say that the value k times a is some integer multiple of pi, which would satisfy sine ka equals 0. Thus, k sub n, for the n possible integer multiples of k, is equal to n times pi divided by a. As a consequence, we can note that these boundary conditions, x equals 0 and x equals a, determine the values of e, which we write as e sub n is equal to h bar times k sub n squared divided by twice the mass. This just leaves us with a quick normalization operation to find the constant a to plug back into our formula. For our normalization, we square our non-zero component of psi and integrate over all space with respect to x. Setting this integral equal to 1 allows us to solve for the constant a. After solving for a, we find that the value of psi sub n of x is equal to the square root of 2 over a times sine of n pi x over a, n is any integer. This little note gives us an infinite set of solutions. The lowest n state in this set is called the ground state, whereas the others are called excited states. There are a few neat details that Griffiths makes note of that are important characteristics of our results. Firstly, the solutions are alternatively even and odd with respect to the center of our potential well. Namely, the result of psi sub 1 is even, psi sub 2 is odd, so on and so forth, etc., etc. When graphing these functions, the number of nodes, or x-intercepts, increases by 1. Psi sub 2 has 3 nodes, psi sub 3 has 4 nodes, so on and so forth, etc. Each of the energy states are mutually orthogonal. What the tar does this mean mathematically? Essentially, we say that two non-zero functions are orthogonal if the integral of their product goes to 0 if they're different functions, but we get a non-zero result for the case where the two are the same function, which would make sense because then we would just be squaring the one and we'd have a probability density. We have a mathematical definition here provided by the University of Lamar. If you're into the abstracts, then this would typically be enough, but we're looking for a physical interpretation of the mathematics at hand. What this means for us is that the two wave functions would correspond to two separate eigenstates if the integral of their product resolves to 0. If they return a constant, then they correspond to the same eigenstate. We can succinctly write this as the Kronecker delta, delta sub mn. Lastly, these solutions are complete. Any other function f of x can be expressed as a linear combination of them. In our case, it looks something like this. We can find our expansion coefficients c sub n using an advanced calculus method called Fourier's trick. I'll find an example and I'll make a video explaining this neat trick later on. Section 2.3, the harmonic oscillator. The last section of this video requires that we look back at our friendly analog of the classical case. If you've taken classical mechanics, you might remember the case of the simple harmonic oscillator governed by Hooke's law. F equals to negative k times x, which is also equal to mass times acceleration. Solving this second-order differential equation yields the general solution of x of t is equal to a sine omega t plus b cosine omega t, where omega is equal to the square root of the quantity of the force constant k divided by mass. The potential energy for the system is a function we will also call v of x, and it's equal to 1/2 times the force constant times the square root of the position. Although for simple calculations this calculation would typically suffice, but we want to be as precise as possible, especially because there really is no such thing as an ideal oscillator. So what we do is we perform some Taylor expansions about its minimum value, and we get an approximation of v of x being about 1/2 times the second derivative of the potential function evaluated at the minimum value x naught times the value of x minus x naught quantity squared. This approximation will appropriately describe simple harmonic motion about the point x naught with a spring constant k about equal to v double prime of x naught. However, lest I remind everyone watching this one more time, we're dealing with the quantum mechanics and not classical mechanics. So instead of looking at an actual spring, we look towards something similar, a wave with an oscillatory frequency omega. In our case, the potential is Vx is equal to 1/2 times the mass times omega quantity squared times x quantity squared. With this, we must solve the Schrödinger equation. Griffith solves it for us two ways. The first way is to use power series expansion, but he opts to show us how he derives his solution using a handy set of operators known as ladder operators. If you would like to, I can make a separate video discussing his analytic solution instead of his algebraic one. That might be reserved for you more interested in mathematic meat and potatoes. Now, let's look at the proof here, shall we? To begin with, what he does is he rewrites our Schrödinger equation in a quote-unquote more suggestive form where we have a separate operator in between our mass quantity and our test function psi, and we set that equal to e times psi. The idea here is essentially to factor out the term within our square brackets. If they were numbers, it would be pretty darn easy and we could just pull out some simple algebra in order to solve it. However, this isn't really the case because we have operators here and not actual, algebraic quantities. So what we have to do is that we have to essentially define some new objects for us that will allow us to make this math a lot easier. And one way we do that is by looking at the expressions a sub plus or minus, which we call our ladder operators. Our ladder operators are exactly equal to the quantity of 1 over the square root of 2 times the mass times h bar divided by our imaginary number I times the derivative with respect to x towards nothing, because once again this is an operator and not like a value, plus or minus I times mass times omega times x. But what's their product? Now, we can have a product of these two particular operators, one being our negative operator and one being our positive operator. And what we do is that we basically throw that onto a ladder function. Now, because these are operators, order does matter. And because order matters, we have to put specifically the negative ladder operator first and then the positive ladder operator. Otherwise, we're going to probably get a different solution, even if they do resolve to be the same thing later on this proof. And I haven't read this in a minute, so I can't recall. That doesn't really matter too much. But anyway, here are the steps that Griffiths takes in order to get his solution, where essentially you just use your standard foiling method through each of the terms. And what it resolves to is a solution of a sub minus a sub plus is equal to 1 over 2 times the mass times the quantity of h divided by I times the derivative with respect to location quantity squared plus m times omega times x quantity squared, all of that quantity plus 1/2 h bar omega. So it doesn't factor perfectly because we have that extra 1/2 h bar omega in there, but we can put that over to the other side and then plug it into the Schrödinger equation, and then we get this result here expressed as a sub minus a sub plus minus 1/2 h bar omega times psi is equal to e psi. Now, what we can do is we can also flip these ladder operators here and multiply them together and get another distinct result by doing the same process over again. And then if we actually take the difference between a sub minus a sub plus and a sub plus a sub minus, we know that that's equal to h bar omega. And with that in mind, we can make some handy dandy substitutions, and then we can actually get a succinct result for a certain step, where Griffiths claims that if psi satisfies the Schrödinger equation with energy E, then A sub plus satisfies the Schrödinger equation with energy E plus h bar omega, which he provides his proof here by basically taking our expression of a plus psi as being our test function instead of just being psi, and then multiplying that through and getting a plus psi times the quantity E plus h bar omega as a result. Now, once again, it does matter which way we order things, because if we order it the other way around, we get a lowering operator instead, where we drop it by a quantity of h bar omega. Now, this basically allows us to say that our a sub minus and a sub plus correspond to the lowering operator and the raising operator, respectively, whereas each of these operators will either lower or raise the energy one particular state to the next within our wave function, which is really handy. However, we can also say that there is a lowest possible state. I mentioned that earlier, our ground states, and we have a mathematic definition for that now, which would be the lowering operator times psi naught, our ground state, should be equal to 0. And he also provides this handy dandy little graph right here to kind of visualize what we're talking about whenever we're saying a ladder operator. Because when we graph it out on certain energy levels, it just kind of looks like a ladder, right? Now, something interesting happens whenever we decide that we want to plug in our ground state back into the Schrödinger equation to solve. When we do so, we actually get a really neat, concise solution of psi naught of x is equal to a naught times an exponential, right? If we want to know the energy of this particular state, we once again plug it back into the Schrödinger equation in the form of this equation here, 2.46, that we were discussing earlier. And when we evaluate it, we get that E naught is equal to 1/2 times h bar omega, which should be our ground state energy for any particle. Now, with our foot securely planted in the bottom rung, as Griffith states, we can simply apply the raising operator to any n numbered state of our wave function, and we can get a distinct energy level for each of these particular excited states of our wave function, which we just simply write as psi sub n of x is equal to a sub n times the raising operator to a power of n times our exponential, where e sub n is equal to n plus 1/2 quantity times h bar omega. And then Griffiths lastly just shows us how to do this with the first excited state, n sub 1, which is right here to my side. And if you wish to copy that down, you may. Voila, there it is. But yeah, that was the first half of our exploration into Chapter 2 of Griffith's Quantum Mechanics. If you have any questions regarding the content that was covered in this video, please let me know in the comments below. I'd love to answer them for you. If there are some problems from this textbook or a textbook that you have that you would like to be looked at or evaluated and for me to make a video on later on, I would be elated to do that for you guys, because I like doing math and walking through steps and trying to show you guys how these systems mathematically work out and how they can give us distinct physical descriptions of reality. Please like the video, subscribe if you haven't, let me know what I can do better, and I will continue this series from here.